Well, hi Randy, this is Chris, and I'm back again. So now that we've done our ultra quick review of the introduction to chemistry, let's go ahead and start talking about chemical reactions real quick, or at least the basics of chemical reactions. Um, so first, I just want to redux the periodic table of elements again, and if you remember, let's just look at hydrogen here. This is gonna be a really important concept. So I look at hydrogen here, and this is the atomic number up here, and then this is the atomic mass, 1.001. If we look at helium, for example, He, it's going to have an atomic number of 2, and it's going to have an atomic mass of 4.0 dot dot dot. So basically, two atomic mass units are the 2 protons, and then there are 2 neutrons in helium, and then there are some isotopes of helium. But we'll just kind of go off of the average atomic mass. So the atomic mass is a very helpful number, and it's going to become very important when we talk about chemical reactions, balancing chemical equations, or what we call stoichiometry. This number right here allows us to convert between the microscopic to the macroscopic world that we live in. And the really cool thing is there's a special number. It's a huge number. It's incredibly large, and this number is known as a mole. Okay. Some people call it Avogadro's number. Okay, Avogadro's number. Okay, Avogadro's number is a mole, and a mole is about 6.02 times 10 to the 23. Okay, so this decimal point's got to move over a whole bunch of times, 23 times, and whatever that number is, that's 1 mole. So it's a huge number. Well, the really cool thing about the mole is if I have a mole of any one of these elements here, so let's say I have a mole, 1 mole, 6.02 times 10 to the 23 atoms of hydrogen, I will have approximately 1 gram of hydrogen. And that's what this atomic mass is really handy for helping out, is if you have an Avogadro's number, a mole of whatever element or whatever atom you're looking at, you will have its atomic mass number in grams. Just like if I had a mole of helium, that would be approximately 4 grams of helium. How cool is that? So if I had 0.5 moles of helium, then I'd have half a mole, so I'd have half of that, so I'd have 2 grams. Okay, so that's a really handy thing to know, and that the concept of a mole is what we can use to convert from the tiny, tiny microscopic atomic world into the macroscopic world that we all know and love. Okay, so let's go ahead and now we will start talking about chemical reactions. Okay. So let's see if I can change this a little bit here. So chemical reactions. Okay. So as you might guess, chemical reactions involve atoms. Okay. And they involve atoms, and really the fundamental thing that is going on, just like we talked about in the last 2 videos, is it involves the electrons. All right, it involves the electrons, and particularly involves the valence electrons. Okay, and it either involves the gain or loss of electrons, or the sharing of electrons, or in some cases we have what are called intermolecular forces, which play a significant role, particularly in the biochemistry and organic chemistry. But we'll get to that. But a chemical reaction involves atoms, and it involves the bonding, the binding together of atoms to make molecules, the breaking down of molecules to make other molecules, or they're breaking individual atoms off of molecules. So chemical reactions really just involve a chemical interaction of atoms. So it's almost all in the electrons. Okay, so a general chemical reaction kind of goes like this. On one side of a chemical reaction, generally we will start on the left-hand side. I will put what are called my reactants. Okay. All right, my reactants. And then my chemical reaction will happen. And on the other side, I'll have whatever the products are. Okay, whatever the products of that chemical reaction are. So let's say that I have an atom A and atom B. Okay, those are my reactants. Then a chemical reaction occurs where atom A and atom B maybe bond. Maybe there's a covalent bond that forms. And at the end of that chemical reaction, I have the product AB. Okay, that's a very simple chemical reaction. Okay, now I could just as easily have a chemical reaction maybe where I have AB. Okay, over here in the reactants, a chemical reaction occurs and my products are A and B. Okay, that's just as easy, or that can happen as well. So don't think it's always just making, making molecules. It can be breaking things down, rearranging, and so on and so forth. But that's basically what we have with a chemical reaction. So the way that chemical reactions, the way that we typically see these things occur, let's see if I can change this up just a little bit. The way that we typically see this occur is we have it all pretty much has to do with energy. So imagine that this my y-axis here is energy, and imagine that my x-axis is time. Okay, and as a general rule of thumb, we're going to start. Remember when electrons like to be toward the ground state, and electrons always like to fill from lower to higher energy levels? Well, chemical reactions are that way as well, that maybe I have my products, and my products start right here, okay, at a relatively high energy. And then what's going to happen is, this is before, so this is before the chemical reaction, and then maybe my, so these are my reactants, all right, my reactants before the chemical reaction, and my products, okay, after the chemical reaction. And you can see that the products are at a lower energy level, and so in this case the products are going to be more stable. Okay, more stable. And I think the intuition is to go, oh, well, then this particular chemical reaction must have proceeded like that. Okay, I started high energy and I went down to lower energy, so some energy, okay, was expelled. Okay, and that's often in this case going to be in the form of heat. Okay, heat is going to be released. The problem is this is not how chemical reactions of this nature typically occur. Okay, this is actually what really happens. So let's draw this again. This is my energy, and this here is time. So what really happens is I'm going to start with my reactants here. Okay, and in order for there to be a chemical reaction, there's what we call an energy barrier. Okay, there is an energy barrier, and I have to get over that barrier. And once I can get over that barrier, then the chemical reaction occurs. Okay, and I have my products, okay, down here, and my reactants up here. Okay, so there needs to be a certain amount of energy. I need to get over this barrier, and this barrier here is known as the activation, okay, the activation energy, okay, and this getting over this energy barrier in a chemical reaction may simply be something as simple as is stirring things up, just adding a little bit of kinetic energy to get things to mix up, and then I get over that hump, and then the reaction occurs. But all chemical reactions have some sort of activation energy. Now, when we see a chemical reaction like this, where the products are at a lower energy than the reactants and they're more stable, that means that I have, at the end of the day, there's a difference of energy, okay? Energy has been given off. So we'll most often expect a chemical reaction like this to be what we call exothermic. An exothermic reaction is a reaction where heat, okay, where heat energy is given off, okay? But for an exothermic reaction to happen, the products have to be at a lower energy level because there's something known as a conservation of energy where you can't just pull energy out of your butt, okay? I have a certain amount of energy here, and I have to account for that energy throughout the reaction, okay? So whatever the difference is from here to here is the actual energy that I've lost, or that has been given off in this exothermic reaction. You know that if you remember the quick clot, back when quick clot first came out and people were getting burned because there's an exothermic reaction. Well, maybe this might be a way of looking at that particular reaction with a quick clot, where you had your reactants, then you had your chemical reaction, you had your products, and you had all this heat released. Now, it is possible to also have, okay, a chemical reaction that is a little different looking, actually, okay, and that chemical reaction might look something like this, okay, where I have my reactants down here, and then I have something that looks like this, and I have my products right here, okay? So this is very different. This is very different from the first chemical reaction that we saw. And as you might guess, here I start at low energy, so the reactants are actually stable. The products are less stable, okay, than the reactants. So this is a chemical reaction where I've had to add energy. Okay, not only do I have significant activation energy barrier, but I have to add energy to these reactants. Okay, maybe I have to really heat them up, or maybe they take heat from the environment, but I have to add energy. This is energy here. This is time. I have to add a significant amount of energy to get to a situation where I have this. So this kind of reaction is often not exothermic, okay? This is what we call endothermic, okay? So when you, for example, somebody sprains or strains their ankle, you often know that we pop an ice pack, and that ice pack gets cold, and as you might guess, this is what that chemical reaction going on inside of that ice pack may look like. That you have reactants, they're becoming products, and that is an endothermic reaction, is actually taking heat out from the environment to get to those products, and so it cools off versus heating up in the other case. Okay, so that's just some critical concepts I wanted to want to talk about: activation energy, exothermic versus endothermic reactions, and then there's one more thing that I want to talk about, and that is the concept of what's known as a catalyst. And a catalyst is something that speeds a chemical reaction up. And in the human body, and when it comes to drugs and toxicology and things like that, these are really important. That's why I'm going to talk about them early. And the most important biological catalysts that our body has is something called an enzyme. Okay, an enzyme. An enzyme in the human body is something that speeds or makes a chemical reaction more efficient. And the way that the enzyme does it is the following. Let's say that I have a chemical reaction in the human body, okay? And it could be any reaction right now that you want to imagine. We'll keep it kind of general at this point. And this is how that chemical reaction would normally be, okay? So here are my reactants, okay, and maybe my products are down here. All right, and this reaction looks something like this. Okay, so you might think that this reaction would occur spontaneously or quite easily in the human body because the products are at a lower energy than the reactants. But here's a problem. I have this really large activation energy, and this is kind of a barrier. This is a barrier to that chemical reaction occurring. And if I don't have enough energy in my body, maybe enough heat or what have you, I may not be able to get these reactants over that barrier for that chemical reaction to occur, even though the chemical reaction would occur spontaneously, and it would occur quickly, and it would be a nice exothermic reaction. It's a matter of getting over that energy barrier. Well, this is where the catalysts come into play, the enzymes in particular in the human body. And what an enzyme does is an enzyme, so I'm going to draw the same chemical reaction in blue here. And so what an enzyme does is an enzyme does not make a chemical reaction happen that wouldn't happen, but rather the enzyme decreases the activation energy. Okay, decreases the activation energy. It makes that barrier much lower, so this chemical reaction can proceed much more efficiently in the human body. Okay, I think I'm going to go ahead and cut it off here. Hopefully that made sense, Randy, and we'll pick it up again talking about specific types of chemical reactions.